Thanks a lot for the kind introduction and for Remark, my favorite band. Let me also thank the organizer for give me the opportunity to talk here. It's a pleasure and a big honor to talk at such an important landmark for the Institute for the Kavli IPMU. So the talk is about, as Kentaro said, some particular class of two-dimensional field theories. This is work in progress with a postdoc here at IPMU, Marco Bertolini, which should be done very soon. However, it's very cautious not to put here the month, but the year only. So let me start. So here's an outline. First, I will describe what are these theories, what are these hybrid 2-2, 0-2 hybrid model things, and what are the correlators of the type 2, and try to say why they are interesting, try to convince you why they are interesting. Then I will move to a very simple application to 0-2 Landau-Ginzburg models. These are a very particular class of models that are very simple, but I think this helps to illustrate many of the properties that abstractly I will review here, or I will mention here. And finally, some future directions. So let me begin here. So first, let's start by describing what are these 2-2 hybrids. The 2-2 hybrids are some two-dimensional field theories with 2,2 supersymmetry. And I will use a very practical approach, and I will say, OK, they are determined by some set of data, but some triplet here. So this triplet is this Y, which is a Keller manifold, W, which is a section of the holomorphic section of the structure sheaf of Y. And I will require this manifold has some C-star action over it, such that when I act on this function, it's quasi-homogeneous. So this triplet is still very, very general. By the way, I mean, this talk is the closest you will get to a Blackboard talk, as you can see. It's still very general to compute anything. So I will actually constrain to this special subset of these models. So first thing, I will take Y to be the total space of some vector bundle over a compact Keller and smooth manifold I call V here. And I will also require that this C-star action, here V is the vector that realizes it, is vertical. It's only act here on the fibers. And this, to get some physics-sensible theories, some physically sensible theories, I will require two extra things. One is that Y is Calabi-Yau, and the other is that the critical points of this function W has a set coincides with B. These models have been around for a while, as you will see in some examples, but very recently there was this paper by Marco and Ilarion and Ronen in 2015, where they started to study very systematically some properties of this model, like a spectrum, etc., and other things. So that kind of inspired us to keep going and studying these models. And next I will tell you also why are these models interesting in physics and mathematics. So the best way is to do it with some examples. So the first example I put here, some of these will be well known for some of you. The first example is kind of extreme case where I take Y to be compact and smooth. Then there's no non-trivial sections of the holomorphic sections of the structure sheaf, and this you land on the well-known case of a sigma model with target space a Calabi-Yau, which is this Y. Another kind of extreme case, if I take this base to be just a point, so there is only trivial bundles over a point, so Y is just a vector, it's a vector space, Cn, and the potential I can write is any polynomial function on n variables. So this is also a very known model called Landau-Ginzburg model. I can also consider the case of orbifolds of Y, and you get Landau-Ginzburg orbifold, so where this gamma is some finite group acting on Y. However, for most of this talk, I will omit any situation where there are orbifolds, because there are many tricky things that happens if you have orbifolds. Maybe at the end I will say some words about that, but in all this talk, we will put under the rug any orbifold. And finally, this example that looks very specific is just these line bundles of a P1. Here there is a potential. Looks a bit complicated, some degree 8 potential. And you can check that the critical points of this is global sections of this space, and you can check that the critical point is exactly this P1. This model, particular, appears has a phase of Kavli, of a smooth Kavli trifold, which is degree 8 hypersurface on this weighted projective space. Meaning the appearing has a phase is some concept that, if you are not familiar, it may be a bit hard to explain, but it's like an alternative description of this Kavli. It's related with a topic called quantum geometry in mathematics. So studying these other phases of geometry, which lives at different points on the stringy Kähler moduli, is a very interesting topic, and it's something I've been studying also. We studied with Kentaro, I studied with David Morrison, and now with Marco, we are looking at these cases. So that's one reason why these models are interesting. As you see, also, they are very general, though. But let's say, let's go to more specific things. So what are the observables? What are the correlators in the title? So first, let me say, due to the supersymmetry of these models, they have a very interesting subset of observables, which are some particular local operators that are in the cohomology of this here, this combination of the supercharges that I'm calling Q bar sub CC. For the expert, this is what defines the so-called CC ring of these theories. And these observables have the nice property that they are close on the OPE. So as the name says, chiral ring, these operators actually form a ring. If you take the product, the OPE, you get this structure constant here. So these structure constants are determined by some 3-point correlators. So these 3-point correlators are holomorphic functions of the parameters of the theory, of the complex structure of the Kavli. I won't enter into pesky details of that. But formally, I can compute them. These correlators I'm writing here, formally, you can compute it with this path integral. You have to consider the V-twisted version of this theory, which is a topological theory, and then you have this, you compute this path integral. So the problem is, okay, so far this is super formal. There's no way to do it just like this. You need to simplify it a little bit. You need to use some tricks that are also, some of them are known for many years. So let's, before talking about the specific form of the correlators, I will say some words about geometric interpretation. So at the beginning, I specify the model by some triplet of geometric objects. Well, the ring also can be interpreted as a geometric object. In particular, if you consider the space of 0n forms valued in wedge in exterior product of the tangent bundle on Y, this is called also the space of polyvector fields, and the delta cohomology, where delta is this Dovaux differential minus contraction with this form that contracts from the superpotential, from this potential, this function W. Then this cohomology, it's isomorphic to this, has a ring. And the operators then, the chiral ring, the operators of the chiral ring can be mapped to elements here on the polyvector field. So here I wrote it in local coordinates. I mean, in a basis, essentially, which is more amenable to physicists. Usually, mathematicians don't like too much this notation, but well, I mean, I wrote the talk. So, and then here, then to demystify this a little bit, let me do an example. Again, a simple example is a Landau-Ginzburg model. If you want, you can consider an orbifold, but as I said, we don't consider orbifolds much in this talk. So Y again, Cn, there is a quasi-homogeneous potential. Then if you compute this ring, this d bar essentially does nothing, and the cohomology is all concentrated on 1 degree and gives you this Jacobian here this, so it's these polynomials modulo these relations coming from the derivatives of W. This is a finite ring. Given this is satisfied, it has finite number of elements, and if you have orbifolds, this is what's called a twisted sector, and you have just to consider the same ring, but the invariance under the gamma action, on the orbifold action. So that's an example of a chiral ring. So now let me, I said what the objects you put on the correlator, so now let me move to the actual correlator, how you compute them. So I will spare you with all the details, and because this is very boring, and I will just give you the result, again, in terms of geometric data. So don't be too scared about all these formulae. The important thing to take here is, okay, you do the V-twist, you use this magic of localization, the theory localized into trivial maps, and you can compute this, it's not so hard, and you get this thing here. So what are the important things to take from this formula? One is this omega y. So this omega y is a top form, holomorphic top form on y. That's, in order for this to be well-defined, you want it to be non-vanishing. The fact that y is Calabi-Yau guarantees that it exists. This e to the L hat is some operator that contracts again from the data. Let me not go into too many details of this operator, but let me point out some things of this formula. First of all, you can see it depends on many things that you actually don't want this thing to depend. For example, it depends here on L, there is this B, which is the volume of the worldsheet. Here, there's also J, which is the derivative of the potential, and I said, okay, you want it to be holomorphic, like at least holomorphic function on the complex structure of Y and holomorphic function of the parameters on W. Well, so there is J bar, so not much good luck with that. And there's also the metric, this G alpha bar appears here, is the metric, this is the metric on Y. So there's many things here that you actually don't want to find. But that will be the next topic, but by now, let me just remark this. If, for example, you take Y compact, this formula reduces to this, which is clearly holomorphic in the parameters. This is a well-known formula. It's from the early days of topological strings. People that have worked on that topic can recognize this. I'm not going to say old people, but people. So I recognize it too. So then, what happened with this formula? So you can say, okay, it depends on many things that I don't want, but okay, let me see if I can simplify it. So one thing you can show in general after some lengthy computation, one lengthy but straightforward computation, is that this formula actually reduces to the integral over the boundary of y with bxi's of some 2d minus 1 form, where d is the dimension of y. And this form here is well defined on this space, which means it's meromorphic on y. So today in the morning also we saw some meromorphic forms, some singularities. So this is some examples of meromorphic form. I don't write the details because it's very ugly, but why I'm mentioning this? Because let's see how this actually helps to clarify this, for example, the holomorphy of this operator. So let me do it in an example. So an example, again, the Landau-Ginzburg case. Take W, now it's again in this Jacobian, so it's just a holomorphic function. So if you do this formula here, it reduces to this thing in this case. Means this boundary, the V is just a point, is the origin, so this thing is some sphere surrounding the origin, and yeah, I should say 2n minus 1. And it's here it's a holomorphic form, which don't worry about the details of this. Sorry, not holomorphic form. It's a meromorphic form here. Don't worry about the details, as I said. But yeah, it's not clearly holomorphic. However, a well-known theorem in the theory of multidimensional residues tells you that you can write this way as an integral over a torus of something that's completely holomorphic. So this formula here that may look very complicated is actually the analogous of in many dimensions of your well-known Cauchy residue. And this formula tells you immediately that the dependence on the parameters is completely holomorphic. So, okay. So in the case of the general case, this boundary looks like a sphere vibration over V. So you don't have actually an analogous of this theorem. So you are kind of doomed there. You cannot write it as an integral over like a holomorphic cycle or something like this. So the best you can do is at the physical level of rigor. You can show that if you take infinitesimal transformations of these parameters, the function remains invariant. So a physical level of rigor means you take the variation and you get an exact form inside the correlator, so it vanishes. So okay, that's for the dependence on these parameters and some connections with some classical mathematical theory of residues, which people like Kyoji is very fond of this type of things. And another property of these correlators that we study, so at the end of the day, you want to compute something. And one thing that makes these things very computable in the previous case was this formula. And in general, one thing that makes them computable is something that we call a transformation law. I'm not going into the details in general because it's very ugly, will be too confusing to introduce it. So I will postpone it until the example, until the application. So that's a simple example where you will see this transformation law in action and hopefully will give you some intuition how it works in the general case. So let me move on to now 0-2 models, so 0-2 hybrids. So 0-2 hybrids are, again, some two-dimensional supersymmetric conformal supersymmetric field theories, but now they have less supersymmetry. That's the 0-2. And they are being studied. These are very new. These are not so much less studied than the other ones. And they are studied in this paper of Marco and Ronen, which is not out yet. I hope it will be out before my paper with Marco. But if you have collaborators, you can have access to the secret archives. So I know what this model is before it gets published, so that we can work on this model. So let me, again, give you the model in terms of some geometric data. So it's very similar than the previous model, but now I have more freedom. Now I have a Keller manifold, but I have the freedom to specify some holomorphic vector bundle over Z. And now there's no potential, but there is a section of the dual of this bundle that they have to specify, and still I require some C-star action, where this J is kind of homogeneous, also satisfies some kind of quasi-homogeneity condition. Put extra conditions as before, set I want to be this total space. But now I have this more complicated condition, which is that I want this determinant bundle of E if B is homomorphic to the dual of the canonical bundle of Z. You will see in a second why this is very important. This implies actually this implies that the total space of E over Z is actually Calabi-Yau. This is another condition that we will not use, but I put it for completeness, which is required to cancellation of some anomaly. And as a small remark here, if you take this epsilon, this E, to be the tangent bundle of Z, the holomorphic tangent bundle of Z, this is actually reduced to the 2-2 case. So that's how you go from this to the previous one. And yeah, you can see this means that the thing is Calabi-Yau, the Y. So okay, so same procedure, but now life is not actually so easy, even though I'm hiding a lot of things here. So one thing is, in general, there is not an analogous of the B-twisted. Well, to begin with, there is not in general, there is not a finite chiral ring. There is an infinite dimensional chiral ring. But in many cases, you can take a subset of operators that close under the product that is very similar to the other chiral ring. It's a finite number. It's called heterotic topological ring. Here I denoted H hat. And you can consider correlation functions of those operators. And there you have some analog of the V twist, which is called here the V half twist, which is guaranteed to exist because of this action, actually. However, life still is very complicated. In general, in this case, the theory doesn't localize to trivial maps. It can have non-trivial maps that are called instanton corrections. We don't know how to compute this in full generality with the instanton correction. However, we have derived conditions necessary but not sufficient for when you can discard the instanton corrections, and many interesting models that are amenable to physics, to Calabi-Yau's, spaces of this quantum geometry, actually doesn't have instanton correction here. But OK, the case without instantons, if you compute the localization ignoring them, you get this formula, very similar to the previous one. I won't go into much details here. This is a new formula. The previous formula in some incarnations has appeared on previous work, but this haven't. And this, one of the main differences is omega now. I cannot use omega of Z because Z I didn't impose that it's Calabi-Yau. So I'm not guaranteed to find a top holomorphic form that's non-vanishing. But in this total space of epsilon over Z, there is one. So this is a section of this, and because the previous condition that we have here, then this non-vanishing form is guaranteed to exist, and I can write this formula. L is a very similar operator. That I will spare you also the details of L now. And the cohomology, the geometric interpretation of this heterotic ring is, again, very similar to the previous polyvector fields, but now it's the natural generalization of 0n forms on set valued on wedge product of this holomorphic bundle E. And the differential is, again, the Dubois differential, but now it's contraction with this J, with this section, which is not necessarily derivative, exterior derivative of another function of this W. So after all this general mambo-jumbo, let me move to a very concrete example where I can illustrate some of the problems and how some of these properties can be used to get a concrete dependence on the parameter of these correlators for some models. So I will give you this example, kind of a very simple example inside this family, we'll call it 02 Landau-Ginzburg model. So as you can imagine, is the 02 version of the Landau-Ginzburg models we saw previously. So take set being C2, so all the bundles there are trivial. So take particular a bundle of rank 3 and this J. So take J, this one. This psi here is just some parameter. You can see now then immediately here that J is not the derivative of a potential plus J to the minus 1 of 0. So the zeros of this section is 0. As before, I'm requiring, remember, that the zeros of J is the base of this set. So here is very simply just the origin. However, there is one thing to remark, that in general in these cases, actually, this way these zeros appear is not a complete intersection. You can see it, you can try to take two of these equations, any two of them, and see the common zeros. You will never get the origin. You really need the three of them. So that's a very interesting thing. I will say why in a second. Here is the ring. The ring already also looks different. There is no orbifold here, but I have stuff on other degrees, not only concentrated on this. So this is like the Jacobian of before, but now I have some things on higher degree. This dA is just a basis of this rank 3 vector bundle, trivial vector bundle I have. I denoted dA. So this vector is already something extra that appears here. And now the interesting thing that I didn't write here, but you can take all this, plug it in on this formula, and try to compute and use these residue theorems that you have for the usual Landau-Ginzburg. Well, it doesn't work. There's reasons why you cannot just apply it. Maybe there are ways to do it, but we couldn't find theorems that help us here. And I mean, it's such a simple generalization. I'm not even going to some very non-trivial set. I mean, it's just flat space. So you cannot use that. So how can you possibly compute these correlators? Well, I can tell you here, and here I will illustrate with so-called transformation law, that, okay, I cannot compute them, but I can tell you what's the dependence on the holomorphic parameters, which is actually what we want. So this transformation law goes into 2 steps. So first step is to find some matrix such that when I multiply it by this vector, you get another vector that's like this, for example, that's independent of psi. This, in general, you can always do, provided the J had the properties I specified before. This UR can found this V is not unique, but you don't care. It's supposed, the thing is supposed to not to depend on the choice of V. And here is what I have to mention. So we expect this actually to be true. This step on the general case, you can always find some V. Now it's harder. You have to find a section of this home from E-dual to E-dual. But in some very non-trivial example, we did it, or more to be more precise, since if you have a good collaborator that's good at computer and stuff, he can do this thing. And it works. You can find it. We don't have proof that exists in this general case, but OK, well, at the end, we are physicists, right? So here, the second step is once you have this matrix, you can then part of the conjecture is you can rewrite this correlator in the following way. So this looks very complicated, but let me just remark. The way you rewrite it is you write exactly the correlator you would have written if this section was T, but you have to slightly modify the insertion. The insertion here, funnily, or like the nice thing is that only depends on the holomorphic parameters now, and I can take them out of the integral. And this takes generically the form of function of psi times, I'm doing very bad with time, or? OK, times a numerical constant. So that's how you do it. Here's an example, so you see I'm not bullshitting. There is this example of correlator is called like psi minus 1 times some number here. So many here, for example, and you can see very explicitly that these numbers are not 0. So in general, we don't know how to do these integrals. These models are not so randomly chosen. They appear recently on some conjectures that some families of these 0-2 Landau-Ginzburg models are conjectured by Abhijit and Pavel to flow in the infrared to coset models. So we expect to have something to say about this conjecture based on these results on correlators. So now, OK, that was for the examples. I hope I illustrate for you some of the toolkits and the properties we have been developing for compute this class of correlators. Let me just now go to mention very briefly the future directions. Some of them are kind of obvious, doesn't mean easy. One is to add boundaries to these theories. So then boundaries, as we saw in the morning in Andrei's talk, means you consider some special objects and boundary conditions that match with some categories. In this case, it's category of global, something is called global matrix factorizations. You can go further and consider defects, which means you put 2 theories separated by some interface. And these defects are very interesting because I just recently learned they are related to 2 categories, which you can ask Misha what are these things, because I really have no idea what they are, but but I know what are defects. So, and finally, the case of the orbifold is actually very tricky. I didn't mention it, as I said. Even on the case of 2-2 Landau-Ginzburg models, these correlators in presence of twisted sectors are in general an open problem. So orbifold is already also a very interesting case where you don't have to, without even considering boundaries. So OK, so the scientific part of the talk is over. but I have one last slide where I will say before showing to you. So the last slide, I put some photos of some things I really enjoyed in my time here at IPMU. But the main purpose of that, and with my colleagues, they will recognize these photos, I'm sure, and these drawings. And the main purpose of the last slide is to say happy 10th anniversary. Thank you for your attention.